Hi, Maria. If you need any help, I'm here. For the technical issues, I'm here. Just to let you know.
So, Kevin, we cannot see your presentation.
Yeah, I'm
Maybe you have to try, let's say, to restart your computer
yeah, that's probably a good idea.
because now you have only 3 minutes. So try to restart now. You have tried all other options. Usually, this is pretty helpful. Okay.
Alexander, shall I try to see
Yes,
if
yes,
I can?
yes, yes. Also, Vangelis, please try.
Entire screen we do, right?
Yes,
Share, and then this needs to be full screen. Do you see anything at full screen?
yes, yes, yes. It's great. I can see it.
Okay.
So, and Vangelis, we will start with you. Then hopefully with Kevin. If there are still technical problems, we will continue with Eric, Dimitris, and as per the program, Fabio is at the end. As I have mentioned a few minutes ago, uh, this session has 5 presentations. Okay, so the instructions provided by the organizers for 15 minutes per presentation plus 10 minutes for questions and answers is going to 25 minutes. And if we will multiply by 5, then it is not possible to fit this into the 90 minutes that we have available. So I have divided 90 minutes by 5, and also there is some time to move from one presentation to the other. So around 17 minutes we have in total per presenter. Okay, so maybe you could try, let's say, to be at not at 15 minutes for the presentation, maybe 12, 13 minutes in order to allow for to, to maybe questions or clarifications if required. Of course, there is a time for follow-up questions afterwards, but can try for this. So it is 3 o'clock here in Greece, so 2 o'clock in Central Europe. I suggest, let's say, to uh, start start now. So, uh, good afternoon. My name is Alexandros Flamos. I'm full professor on Techno-economics of Energy Systems at the University of Piraeus, and I am director of TISLab, the Energy Modeling, Strategy and Policy Analysis Laboratory of University of Piraeus. Currently, we are running 13 projects funded by the European Commission, and one is funded by the Swiss Federal Office of Energy, all in the fields of techno-economic analysis of energy systems and the support of effective energy and climate policy design. In this conference, I participate mainly through the Horizon 2020 Sentinel project, in which I participate as partners, and we lead the case studies. I will chair this session, and I'm glad to open it now. Aim of this session is the development of an enhanced understanding of national and subnational transformation pathways, focusing on European countries and how this can pave the way towards meeting the EU net zero goals by mid-century, the development of plausible pathways for meeting the ambitious decarbonization targets was already challenging, and now following the invasion of Russia to Ukraine and the consequent energy crisis, we have the additional challenge of handling the increased uncertainty and the pressing need of finding viable solutions for covering energy demand in the short term without falling in the trap of a long-term lock-in to carbon emitting technologies. Now, I don't want to take more of your time. As I mentioned, the time is pretty, let's say, the time frame is pretty stringent. So let's move forward to Dr. Evangelos Panos. Vangelis is a senior researcher at the Paul Scherrer Institute, and he will present Switzerland's national mitigation pathways towards net zero CO2 emissions in 2050. So, Vangelis, the floor is yours.
Thank you, Alexander, for the nice introduction. And I would like to note that I'm very happy that we collaborate with Alexandros in our Swiss energy projects. So I'm going to share my screen and I'm going to travel you to Switzerland, which is a small country in the center of Europe, famous for chocolate and cheese. But also it's famous for one more additional issue, which many countries in Europe are trying to achieve in 2030 and 2050. And this is that Switzerland has a very low emissions from power generation. Is this blue here? I'm not so sure if I can put a pointer. One moment. Yep, here. So the power generation sector of Switzerland is almost carbon free. It's less than 2 megatons per year, and this is only for waste. Switzerland has committed to net zero CO2 emissions in 2050, but as you can see here on the left-hand side, there are some challenges, and these are the limited renewable resources. Practically, wind is very underdeveloped in the country, and hydro is very well developed and cannot be expanded anymore. So the additional renewable resources in Switzerland is mainly solar PV, which means that the country will face seasonal together with a daily balancing, because 56% of the electricity in Switzerland comes from hydropower. Hydropower is mostly available in summer when the snow melts in the mountains, so there is plenty of water. And you can imagine that if Switzerland develops further the solar PV technology, then it will be excess of electricity in summer, while in winter the country remains importer of electricity. There is an issue with CO2 storage. The sites are very limited, underexplored. The latest estimation potential is about 50 megatons cumulative potential for CO2, which is about one gas power plant running for 20 years equipped with CO2 capture and storage. There is a large population increase is expected for the next 30 years. More than 20% is the highest among the Western European countries. And of course, there is an energy security issue. As you can see on the graph on the right-hand side, the country has achieved quite a significant reduction in the CO2 emissions in the last 10 years, especially from the residential and services sector. And this is because of a set of policies that are in place since 2010. So in 2010, Switzerland introduced a carbon tax at 36 francs. A franc is roughly equivalent to €1 per ton of CO2, now is 120. In 2011, started the negotiations to link the Swiss European trading system with the European trading system, and this negotiation successfully concluded in 2020. In 2015, Switzerland was the first country submitting its climate action plan ahead of the Paris Agreement. In 2018, Switzerland entered the new Energy Act into force to increase the energy efficiency, to increase the renewables, and to withdraw from nuclear power, which currently supplies 40% of the electricity. The country committed to net zero emissions in 2020, but in 2021, the Swiss voters rejected the CO2 law, which was seen as the first step towards the net zero emissions. In order to tackle this challenge, how Switzerland can achieve in a technical feasible way the net zero transition, the Swiss Innovation Agency funded with 250 million francs from 2013 to 2020 8 research projects looking at biomass, storage, industry, buildings, transport, electricity grids, and society. One of them, the so-called Swiss Competence Center Joint Activity Scenarios and Modeling, it was a cross project of all these individual projects to assess net zero pathways. And I'm going to present results from this project. So I'm going to focus on 3 scenarios from that assessed, 3 pathways that assessed in this project. A core scenario that is a cost optimal, let's say, trajectory towards net zero. An anti-scenario which assumes a society and lifestyle is fragmented, so the people are not so supported towards net transition because of, let's say, affordability issues, and the energy security scenario, which is a scenario that achieves 0 net imports of energy, and the society is willing to pay for more security. The tool that we use for that is the Swiss Times Energy Systems model that models the entire Swiss energy system, and it has a long time horizon with 288 hourly time steps. I'm going to say more details about the times framework for the sake of time. I will go directly to some key results. So the cost optimal trajectory, which is the key scenario, regarding achieving net zero emissions in 2050 suggests that industry, services, residential and transport sector need to fully decarbonize, while any remaining emissions from industry need to be offset by CCS and PECs in the energy sector. The challenge here is mainly the speed of the transition, because in the next 10 years, Switzerland needs to have 3 more times heat pumps in buildings, electric cars in car sales, and installed solar PV power compared to today. It is on track on achieving the electric vehicles in car sales and the solar PV deployment, but lags behind at the moment in accelerating the renovations and heating equipment replacement in buildings. The things become a little bit more stringent and more demanding towards 2050, because heat pumps needs to be deployed to 75% of the building stock, while additional energy carriers like hydrogen need to be deployed, and CO2 emissions of 9 megaton need to be captured. This will lead to a 2,000 per capita society. 2,000 watt per capita is the average consumption per capita today in the world, a global average. So this means that we need to deploy a lot of efficiency measures. In terms of sectoral developments, the electricity supply sector becomes more weather dependent. The orange, which is the nuclear, is phased out by 2040 and is replaced on energy basis by wind and solar. While in the electricity demand, we see that industry, services, and residential sectors, more or less due to energy efficiency, keep the electricity demand stable, while the additional electricity consumption mainly comes from the transport sector, 14 terawatt hours, and from electrolysis, 9 terawatt hours. And from these 14 terawatt hours in the transport sector, around 8 terawatt hours comes from private cars, around 4 comes from rail, and the rest is from the other sectors of transport. And these electric cars will require 6 gigawatt peak for charging in 2050. Which means because of the more weather-dependent supply, the electricity system becomes more seasonal imbalanced than today. And you can see here that in summer, there will be 7 terawatt hours of excess electricity power that goes actually to electrolysis. And electrolyzers in summer operate at a base load, while in winter, still Switzerland remains a net importer of electricity. These imbalances need to be tackled by deployment of flexibility options at different scales, from pump storage and stationary batteries to thermal storage, which becomes very important, to hydrogen storage, vehicle-to-grid, ancillary services, reserve demands, and demand shift. About 13% of the electric car need to go to vehicle-to-grid schemes, and about 10% of the electricity demand need to be shifted at hourly basis. The CO2 emissions that need to be captured are around 9 megatons, 8.6 to be precise, of which about 4 are negative emissions. The CO2 domestically sequestrated potential is exploited. This corresponds about, as I said, is 50 megatons total. This is about 2 megatons per year, which means that the rest need to be exported or traded, which is a challenge because this will require access to international CO2 storage sites to be secured. Now the question is, what happens if the renewable energy uptake is slower, if the population doesn't follow this cost optimal development? And this is insights from the anti-scenario. And we can see here that in the electricity supply, we have a deficit of 11 terawatt hours because of the less development of renewable energy. This primarily impacts the hydrogen sector. You can see that the domestic hydrogen supply drops from 42 petajoules to 12 petajoules and is mostly limited to biomass with CCS to offset any emissions from the building sector. Also, in such a scenario where the renewable energy uptake is slow, the energy efficiency needs to accelerate. And we can see here in this comparison between the CLI, the cost optimal, and the anti, the scenario with the less development of renewable energy, that the residential final energy consumption drops by 20 petajoules, and residential, the buildings, bear most of the effort, which implies that the building renovations need to be brought a decade forward. This is here, the space heating demand per kilowatt hour. In the cost optimal trajectory in 2050 is about 60. This is a modeled result. But in the case where the renewable energy uptake is lower, these are brought forward by a decade. And the other question that I would like to put some insights is, can we achieve the net zero and be self-sufficient? So this is the secure scenario. And in the secure scenario, basically the secure scenario reduces the gas imports to the half in 2030 from today, with the aim in the 2050 Switzerland to have almost 0% import dependency. Still, however, this 0% import dependency is not achieved because we will need biofuels and e-fuel imports. I will skip this result here for the sake of time. What I would like to show in such a scenario is also that Switzerland needs to develop synthetic fuels. And in fact, in 2050, domestic synthetic fuel consumption, because in a zero import dependency scenario, it's zero import of all energy carriers, it's not only electricity or biomass, but also hydrogen. So everything in this scenario needs to be produced domestically, any molecules that the industry is needed. And this domestic synthetic fuel production covers about 90% of the imported gases that are otherwise occur in the cost optimal trajectory. So what are the costs for that? The costs range, the costs are compared to a baseline that achieve already a 40% CO2 emissions reduction. So these costs range from 300 to 1,400, depending on what conditions we assume what context we assume when we achieve this transition. And I'm come to the conclusions. So in Switzerland, the net zero is technically feasible under some key points: that we have coordinated sectoral policies, that we accelerate the deployment of domestic renewable resources by doubling the renewable capacity every 10 years, by doing higher efficiency in buildings, by saving 7 to 11 terawatt hours per year, and by shifting the remaining potential of bioenergy from the end-use sectors to energy supply with CCS to offset negative emissions. So 2/3 of the total consumption of bioenergy needs to go to the supply side. The net zero systems will require flexibility options provided by all actors, and in this context, thermal storage has equal importance with electricity storage. Hydrogen makes achievable both net zero emissions and import independency, but it comes at a cost. There are large power-to-X investment needs. About 1/3 of the energy system-wide capex is going to power 2x in such a scenario. But without hydrogen, the net zero target is not feasible for Switzerland. And what it came out as shortcomings of this analysis that triggers future work is that we need to work further to improve the realism of the modeled pathways, not only the technical, but also the societal. We need to increase modeling details when it comes to net zero to identify local constraints and best fit options, and also to develop participatory processes in scenario development and communication. So that's all from my side. I hope that I kept a little bit the time, and I'm happy to open questions.
Thank you very much, Evangelos, for your insightful study and nice presentation.
Sorry for running so much.
No, no, no. This is exactly what I have asked for. So thank you very much for keeping the time. I see that there are 24 people in the call. So if there are any questions from the audience, please raise your hand or write the question at the chat. And okay, Evangelos will provide the answer. Up to, let's say, one question that I have, Evangelos, is regarding the current energy crisis and all past assumptions or most of the assumptions are changed. So, for your study, are you considering, let's say, the implications of energy crisis, increased prices, or not?
Yes, this study occurred between 2017 and 2020, so COVID effects and energy crisis are not there. However, we had a scenario that, as I thought, reduces the import dependency. Of course, it's not the same, but some insights of what happens in such a case where we want to be less dependent on gas can be drawn from this scenario. But explicitly, the current crisis is not taken into account.
Okay, I fully understand. This is a difficulty that we face in our modeling exercises. And regarding the sectoral policies accounting for systemic interdependencies, can be considered the most effective to reach net zero?
Yes. So what we noticed from this study is that the CO2 law that it was rejected by the people was foreseen to have some standards in buildings and cars. But it proved out through this analysis that these standards, if imposed in an uncoordinated manner, maybe you made them more stringent or less stringent than is needed. And this is a lesson that we took out of these scenarios, that the scenario that implemented exactly the law tend to be more expensive than a scenario which is a little bit more relaxing on the stringency of the implementation of these standards.
Thank you. Thank you, Vangelis. So, if there is no other question, I don't hear something and I don't see something in the chat. So, let's try with Kevin. If
And
we
I would like to apologize that I have to leave for another meeting. I'm very sorry for that. Thank you very much for being in my presentation.
thank you, Vangelis. You are aware of the situation. Everything
Thank
is
you, Alexander.
fine.
Thank
Thank
you.
you. Goodbye. So, let's move to the next speaker, Dr. Kevin Forbes. Kevin,
See, my apologies for my camera not working. Can you see my screen?
no, no. Are you sharing your PowerPoint presentation?
Yes, I'm sharing, attempting to share my PowerPoint here. It's a wonderful PowerPoint.
Unfortunately, we
Let me
cannot see.
try one more.
Kevin,
Yeah,
we can, let's say, go to the next
yes.
presenter.
Why don't you try going to the next speaker, and maybe I can pull a rabbit out of the hat. at a later point.
Yes, yes. Try to resolve these technical issues, and then we'll continue with you. Okay.
Yes, yes.
So thank you very much. So
Thank you.
we will continue with Eric Francisco Alvarez. Alvarez is assistant researcher at Comilas Pontifical University, and Eric will present a methodology for the impact assessment of local energy communities on the expansion of centralized storage and the grid, as well as the operation of the system in Norway and Spain. So, Eric, uh, the floor is yours.
Thank you for this introduction. Can you see my screen?
Yes, great.
Okay, thank you. Yeah, this presentation is about a methodology for the impact assessment of local energy communities on the expansion of centralized storage and also the grid for all the European system and scale European system, but with the increase in the details in Norway and Spain. Okay, in these presentations, okay, I'm making this presentation, but this work is also developed by Sebastian, Sara, Ingeborg, Luis, and Andres. And this work is also between the cases within the case study 3 of the Open Entrance project. This is a European project, and this methodology involves these three models: the OpenTPS, Gusto, and EMPSW, that together will be able to provide the necessary details of system planning and operation. The EMPSW will undertake the general definition of the hydrothermal system studied, while Gusto will deal with the deployment of energy communities and the optimal use of the resources within them and under several different strategies. And the OpenTPS will incorporate the impact of the transmission grid, which can be enabled able to make a long-range use of resources across the European Union or the European scale system. This is a work in progress within the case study 3. And so the scope of the study is about the analysis of the impact on the system operation costs and the transmission network expansion, and also under several combination of capacities of hydro pump storage and the deployment of local energy communities. And why? Because it's like we're trying to investigate the flexibility provided by local energy communities, and also can be a substitute or complementary for the flexibility provided by the pump hydro storage, and also the flexibility provided by the grid. No? There is several storage technologies we are considering. It's like the pump hydro storage, hydrogen, etc. No, but in different time scales, seasonal, weekly, daily. No, and I should say that with different size of the storage as well. And the deployment of additional storage is assessed principally in Spain and also in Norway. But the rest of Europe system is like will only represent in aggregated level. Yeah, this is the scope of the study, and some expected results of the case study, and also from this methodology is about, for example, the optimal operation of the power system in aggregated and also in local levels, and also for all the system, but also for all these scenarios that we are considering with different capacities of the pump storage, and also for the local energy communities. And also an ultimate development of the transmission network, with also to put in a context that is like, okay, we need some lines, for example, within Norway and Central Europe, or also Spain with also Central Europe. Based on the previous two results, is like we may, for example, we can get an analysis. We can make an analysis to determine the impact of the system operation and network development associated with a trade-off with this different capacity of storage, and also the deployment with also different levels of the deployment of local energy communities. These three models are working with a soft linking approach, and also connected with an open entrance platform. This connection is we receive some data from the open entrance platform in order, for example, to build that the system, and also with all additional data that we provide from the on databases of every model, and we exchange data. We exchange data from the model, from the EMPS that provide, for example, the hydro operation and electricity prices for Gusto and OpenTepes. And also, for example, Gusto can provide modify electricity profiles related to the energy communities that will be assessed. And OpenTepes will provide, for example, the new expansion plan for transmission. This European scale electricity network that I talked before is like, has a process. No? As I told you, we importing data from the open entrance platform, downloading, transforming via Greeks, and also this data that we download, we distribute it across all nodes. That we also taking this spatial distribution from the eHighways network. And considering these next two regions, inside of every next two region, we considering local energy communities, no? And also we increase the detail of the system representation in Spain and Norway, modeling, for example, the hydro network and the storage management. Some probabilistic scenarios that are related to the hydro inflows. General future about for the European scale system is about a scenario. This scenario techno-friendly to reach the 1.5 degrees target. It's one of the scenarios that is in the open entrance project. Is more details about the scenarios can be appreciated in this paper. This scenario is trying to emphasize the smart society and also technology novelty. The European system is also in a static planning with a 1 year, 2030, with hourly resolution. In an investment related, for example, for the transmission lines in this AC and DC and hydro pump storage unit. The main data related to the system is related, for example, data that come from the open entrance scenario, installed capacities per country and per technology in 2030, and also the electricity demand per country and also per use in 2030, and the net electricity production for all the technologies. No, but this is in great numbers. No, we need to distribute it because like we have several nodes, and is, for example, there is some parameters that are not contemplated in the open entrance scenarios, and that we also need, for example, these boundaries and power exchanges, electricity demand profile correlated to temperature time series, and some technical parameters and financial about the generation, transmission, storage, and technical parameters related to the hydro technology, the hydro network, etc. And some also theoretical potential for the demand response, and also related to the energy communities. Some preliminary results about it is like the determination of the potentials of the energy communities and how they can modify the net electricity demand in Norway and in Spain. But for example, this is the methodology that we adopt for this determine the potential of the energy communities. With the certain patterns, and determining also the model energy communities, and also to use this an optimization model to determine the optimal use of the resources within the energy communities. There is some plots like here, like for example, there is a potential of the different energy communities in Norway, and also in this other plot we can appreciate that, for example, the modification of the demand from and energy communities related to the energy communities. More details about it is also can be found in this paper. about energy communities and its impacts on the electricity demand. And the next slide is about that some other, for example, the network already. This is the network that we have already, and it's on a scale, a European scale network. It's a with hourly resolution, and we have some, for example, all the electricity production per technology for all the system. This we can see that for the 2030 there is a significant amount for renewables, a participation also from gas, more or less, and also for the hydro resources as well. And then this slide, for example, is like hourly electricity production, including the discharging of technology storage. We can appreciate differences between, for example, winter days and summer days, and specifically for a month in January and other for August. No, good participation in August for solar technologies, and that also replace more or less all the gas technologies and thermal technologies. And in winters, it is needed. That is I have from now, and so thank you for being in my presentation.
Many thanks for the presentation, Eric. Indeed, this is a very timely study, taking into account the importance of flexibility, storage, in the way towards decarbonization, especially now with the uncertainty of gas supply and the supply through pipelines and also the LNG terminals. Again, if there are any questions from the audience, please feel free to, to ask. You can write the question on the chat or directly raise the question. I don't hear something. I will give some time to the audience. Eric, one question is, what is the starting and the ending point of the modeling framework? So I understand that there is a soft linking of models taking place for this exercise, and is there an iterative procedure for this study?
Yeah. In the workflow, it's like I present the workflow between the models. The starting point is about, for example, to the expansion of the transmission that we started with this point, because like without the transmission, we will get some load shedding for any parts. And so, because if we are talking about the future, we are talking about the 2030. And after that, to increase the detail with a hydrothermal operation, that is also one big constraint for the system operation. And after that, it's like we increase the detail in order, for example, to modify the electricity profile from the provided for the gusto that is related to the energy communities. And we started again with an expansion of the transmission. And we, at the end, we converge with we comparing the electricity productions. When we don't find any more differences between the electricity productions, we stop.
Very nice. And are you considering as for energy storage other types besides pumped hydro, like for example hydrogen batteries?
Yeah, we're considering batteries, hydrogen, pump storage, also compressed air storage as well. Yeah, that's all the storage knowledge. Hydro reservoirs as well. That is also important, but this is like a utility at the end, no? But yeah, we're considering this kind of storage, like in seasonal, weekly, and daily, no? In this wide range of that we can get the flexibility in different time scales.
Okay, great. Thank you very much. Is there any question? I see here something from Sing Juan. Chen, would you like to raise the question directly, or
Yeah, I just yeah wonder if how do you take the consideration of the future electricity transmission expand, and also this is maybe linked to import and export of electricity in different countries, and yeah, is there any assumption you made there, or is based on what we have now in Europe?
You mean the consideration of the candidates, how I generate the candidates for that, or?
The transmission between the countries, so
Yeah.
like import and export. Yeah.
Okay. At the beginning, we also performed, and I haven't talked about it, but it's like we considering a methodology for determine the candidates, the optimal candidate between the cross borders, and also between the countries, because there is some regions that we are not considering only one node. There is several nodes in country, and we have to, for example, to determine what is the optimal ways between these nodes between the countries and also cross countries. We determine by the longitude of the longitude of the line, and also we related to the cost of the longitude, and also determine for some projects that are considering to be implemented in the future, with some uncertainty, clearly. Not the projects that are totally clear now that to be implemented, other projects that are all in studies, no? And so in this way, we have a portfolio to make this kind of investments.
Yeah, thank you. So, do you consider the geopolitical situation for now? For example, there's war coming on and going on, and maybe the people are having more issues about importing energy from other countries, and yeah.
Yeah, this is also one of our objectives, because Norway can be a good exporter, for example, to Central Europe. And we be careful to study what projects and what lines can be also implemented, and also considering like a candidates in the European scale system. And also Spain can be also a exporter as well, and importer. That is a different kind, because it's like in Spain there is more potential to implement solar plants, solar plant unions, solar plants and pumped storage hydro than in Norway. And so this is a different situation between them. But the local energy communities also play a big role, because it's like, okay, they can modify the electricity production and not, I'm sorry, the electricity profiles between a specific seasons of the year, and can play, for example, a role to be substitute some investments at the end.
Yeah. Okay. Thank you.
Mm-hmm.
Thank you very much indeed. Very fruitful discussions, of course, to be continued. Also following this very, let's say, inspiring event. And now let's move to the next presentation of Mr. Dimitris Papadonis. Dimitris Papadonis is associate researcher at TISLAB University of Piraeus, and Dimitris will make a presentation about the energy transition in the residential sector in Greece, trying to reply if the current planning for natural gas is working, or we should invest in electrification. So, Dimitris, the floor is yours.
Yes, thank you very much for the introduction. I'm about to present you our work conducted under the Sentinel project, an Horizon 2020 project that aims to enhance the role of modeling in support of the transition to a low carbon energy system in Europe. I'm about to skip the European context, the current policy context, that because of the time, and I assume that most of you will be aware of it. So I'll pass straight to the Greek context, in which, and especially the Greek building sector, which consists mainly of aged buildings, and the residential one, which consumes around 25 of the final energy consumption, and it needs immediate renovation, as it's considered more than critical for the achievement of Greece's energy transition and security, especially in this ongoing energy crisis. So, towards the decarbonization and the energy transition of the Greek residential sector, the current National Energy and Climate Plan, the NECP, sets as an objective that by 2030, 12 to 15% of the total number of dwellings in the country, i.e., up to 60,000 homes per year, will be upgraded in terms of energy efficiency in part or in full, also focusing on investing on natural gas. So, in view of the plan's forthcoming amendment, we seek to understand whether the current renovation rates have the ability to decarbonize the sector, and whether, in view of the latest developments, should Greece proceed with investing in natural gas as a transition fuel, also increasing its energy dependence. So, to address this question, we make use of the DREAM model, a model that is part of our laboratory's modeling suite, and participates in around 10 Horizon and live programs projects on the time. DREAM is a hybrid bottom-up model combining key elements of both engineering and statistical models, and among others, it can simulate the energy demand of buildings. In this study, the model is used to simulate the energy demand of the Greek residential sector, configured according to available research and demographic data. Again, in the sake of time, I will not be so detailed on how we model the sector, maybe in the questions later. So, to explore the energy transition of the residential sector towards 2050, we simulated 4 scenarios based on the current NECP annual renovation rate of 60,000 homes per year. More specifically, the first scenario is based on the current NECP targets, which mainly focus on using natural gas as a transition fuel, while scenarios 2, 3, and 4 are focused on investing in electrification and differing on when the natural gas phase-out processes start. In the second scenario, the natural gas phase-out process starts at 2036, in the third scenario at 2031, and in the fourth scenario at 2023. In all scenarios, the dwellings that have their the heating technology system change also have, and they are built before 1981, also have their exterior walls insulated and their windows replaced, while dwellings that are built in the period 1981 to 2000 have only the exterior walls insulated. So, a first interesting observation from the simulation of these 4 scenarios is that we see that electrification scenarios lead to lower total energy consumption when compared to investing in natural gas as a transition fuel. While with these renovation rates, we see that the electrification scenarios 2, 3, and 4 lead to approximately the same final energy consumption. However, the most interesting observation of the simulation of these 4 scenarios is that no matter on what fuel we invest on, natural gas or electrification, we invest mostly on, with this renovation rate, none of these 4 scenarios can achieve the decarbonization of the residential sector in Greece by 2050. And another interesting finding is that among the 4 scenarios, the first scenario, the scenario that invests on natural gas mostly, is the one in which fossil fuels are mostly used. So, after observing this, we confronted the crucial question on how Greece could achieve decarbonization of the sector, of the residential sector. And we aim to answer this question implementing a reverse engineering process. So we again made use of the dream model, but in this time we formulated new scenarios beyond the specifications of the current NECP scenario with a target to see when and how we can decarbonize the sector. So we formulated scenarios 5 and 6, in which we explore which is the appropriate renovation rate for the sector to be decarbonized by 2050 and 2040, respectively. And we also investigate the environmental and financial impacts of investing in natural gas or electrification. So we have scenario 5, that you can see in the slide, in which we investigated decarbonization of the sector by 2050 with two different pathways. The scenario 5A, in which we invest in natural gas by 2030, and the scenario 5B, in which we invest in electrification from the beginning. Here we see that to achieve decarbonization, we need 1,000 dwellings renovated per year instead of the 60,000 the 60,000 dwellings per year renovation rate, which is currently planned. And to achieve decarbonization by 2040, scenario 6, we again we simulate two different pathways: one that focuses on natural gas, on investing on natural gas by 2030, and one that focuses on investing in electrification from the beginning. So in this case, we found that we need 145,000 homes to be renovated yearly, and the outcomes of this process can be seen in this slide, in which indeed we see that scenarios 5A and 5B with these renovation rates decarbonize the sector by 2050, as we have no consumption coming from oil products or natural gas, and scenarios 6A and 6B indeed decarbonize the sector by 2040, as in this case, from this time and then, consumption from oil fuels is also eliminated. After this, we conducted an environmental analysis, and we found that towards the decarbonization process, investing in electrification leads to less harmful environmental footprint as more tons of CO2 are avoided. Indicatively, we notice that when comparing, for example, scenarios 5A and 5B, i.e. the decarbonization of the sector by 2050, we see that when focusing on electrification, more than 16 million tons of CO2 are avoided by 2050. Of course, we also identify that when decarbonizing the sector by 2040, scenarios 6A and 6B, instead of by 2050, scenarios 5A and 5B, the environmental benefits also increase. Apart from the environmental footprint, we also investigated the financial impact of each decarbonization scenario based on the estimations of the evolution of energy, technological, and building sectors' ETS costs. Based on those, we estimated the fuel and electricity costs and the fuel cost savings towards the transition towards 2050. As you can see, when comparing each decarbonization scenario in terms of focusing on natural gas or electrification, again, we find out that investing in electrification leads to less total fuel costs, while we also find out that when decarbonizing the sector by 2040, this increases the fuel cost savings compared to decarbonizing the sector by 2050. Moreover, we investigate what's going on with the renovation costs, and we also find out that in each decarbonization scenario, electrification leads to lower the renovation costs due to the fact that with investing in electrification from the beginning, we avoid to implement twice a technology change in the household in the same household twice. Sorry, because from the beginning we focus on one technology, the heat pumps. So, moreover, considering the latest announcements of the European Commission about including the building sector and therefore the residential one in a parallel ETS cost system, and taking also into account that these charges will probably be undertaken by households, we made sure to calculate how this inclusion will affect households in its different scenario. Again, we found out that when comparing the decarbonization scenarios, decarbonizing the sector by 2040 leads to lower annual and total costs, ETS relevant costs for the households, while similar is the case when focusing on electrification. So, to sum up, after this, we summed up all these costs, the fuel costs, the renovation costs, and the ETS relevant costs, to conduct a cross-scenario comparison about the total annual cost at household level in each scenario. Again, we found out that electrification leads to lower total charges per household, while again, the decarbonization by 2040 also reduces costs. This analysis was then done at the national level, leading us to the same finding that decarbonizing the sector earlier by 2040 and focusing on electrification increases cost savings, among with all the other benefits that, without taking account all the other benefits that decarbonizing the sector earlier may provide us. So, overall, our study aims to shed light on energy transition pathways in the Greek residential sector, aiming to provide useful conclusions and recommendations to the national policymakers and other relevant end users from the field of policy and practice, especially in view of the latest evolutions in the energy markets, as well as the forthcoming amendment of the Greek NECP. Our results indicate that by following the current NECP rates, we will not achieve decarbonization, and if we want to achieve it, we should increase the renovation rate from 1.5 to 2.5 to decarbonize the sector by 2050, and 3.5 to decarbonize the sector by 2040. Also, we also identified that to achieve decarbonization, investing in electrification leads to lower ETS, fuel, and renovation costs, and thus lower total costs, both at the household and the national level, in comparison with investing in natural gas. Almost similar is the case when decarbonizing the sector by 2040, where we see that the total costs, both at the household and the national level, also decrease. In total, in view also of the latest energy crisis, our findings highlight the need for more aggressive and ambitious policy measures and decisions with long-term impact, instead of focusing on horizontal short-term measures that do not address deeply the energy transition challenges, as, for example, the phenomenon of energy poverty. Here is the team the TISLAB UPRC team that conducted this study, and contact info, also accompanied with information about the project and the deliverable that this work is included in. Thank you very much.
Thank you very much, Dimitris. Indeed, very useful outcomes, especially taking into account that the National Energy and Climate Plan in Greece is currently under, let's say, update, as it is, of course, in most EU countries. And your study provides very useful insights. Now, one question that, but let's first take some questions from the audience. I see here a question from Mr. Nikolaos Kleanthis. Nikos, would you like to directly raise the question to Dimitris? We cannot hear Nikos. Okay, so I will transfer the question. Nikos is asking if you are considering modeling electrification scenarios that explore potential synergies between heat pumps and solar PV in a roof for self generation, consumption of electricity in a household. So this is one question. I know the answer, but Dimitris will reply. And in addition to this question, Dimitris, maybe you can give, let's say, provide some information on how energy crisis and skyrocketing gas prices have affected your analysis. So, Dimitris?
Okay, I'll start with the audience question. In that point, we do not examine this correlation between heat pumps and solar PVs, but it is we are about to conduct this study, also including issues of storage, electric vehicle, electric EV charges, and to better identify the consequences of this process during the energy transition. And to what concern the second question, we conducted this study with energy, with the latest energy prices. We have taken into account prices from April 22 in Greece, which are increased, which are the new prices on the electricity and fuel costs, and for their evolution, we took these prices as an initial value, and we expanded it through the predictions that the long-term strategy of Greece towards 2050 provides us. Of course, it is uncertain, but we think that this is the most close to reality that we could imagine
Okay.
in this uncertain context.
Yes, yes. Uncertainties are at extreme levels. So thank you very much, Dimitris. And now we will make, let's say, a third attempt to hear Dr. Kevin Forbes. So, Kevin, have you resolved the issues?
No, but just let me just give you a 15-second overview of what I've done. Is that okay?
Or more, Kevin, or more. So
Oh, okay.
you may, let's say, describe your study. It is a pity we cannot see your PowerPoint, your video, but take some time, let's say, to present
Okay.
your
So
study.
the concept here is we've had a massive change in the electricity industry towards distributed generation. And the existing framework of load forecasting isn't equipped to handle that. That you have distributed solar and wind energy giving rise to generation at the distribution stage as opposed to the high voltage stage. And the system operator doesn't have that information on what the distributed generation is going to be. And what happens is, in the case of, let's say, solar, a homeowner with solar panels will rely on grid supplied load when solar conditions are unfavorable, but will rely on generation from his or her solar panels when the solar conditions are favorable. This makes forecasting load by the system operator more challenging when traditional forecasting approaches are employed. And I went out, I got some data from Great Britain, and the load forecasting error since 2010 has almost doubled. And part of the reason for this is because you have these distributed solar, distributed wind production taking place that the system operator doesn't have complete information on. And so my idea in the paper is a solution to this using data from Ireland, where we have lots of wind energy, and most of this wind energy occurs at the distribution stage, where the system operator really has no control. There's not much in the way of solar, but it's coming. And what I note in the paper is that you have these load forecasting errors that in some cases are just simply huge. And what I do is I estimate what's called an arch RMAX model. And the RMAX part of it takes into account that you have conditional heteroscedasticity, that you have this volatility in electricity consumption. The RMAX part of it is that there's this easily understood autoregressive nature to electricity consumption. That the amount that you consume at 2 p.m. today is correlated with what you consumed yesterday at the same time. And we can exploit this to come up with better predictions, especially if we include in our model, or I include in my model, the forecasted meteorological conditions. And that's what I do. And I estimate the model using about 33,000 observations and 50,000 observations. And then I test my model using the 33,000 observations. And what I find out is that the model predictions are more accurate than what the system operator is working with. And so that's the potential contribution of the paper, that we can use time series methods to help ease the energy transition. That you have this distributed solar and wind, it doesn't fit in with the old regime. We can use econometric methods to help improve matters. End the story. Thank you very much.
Thank you very much, Kevin. It's a pity we cannot see your
Yeah, I'm very
PowerPoint,
but
but
my
you know,
apologies for my technological failure on this end. I think it's related to the fact that I don't have dedicated internet service at this new location that I moved into.
okay, but following the, let's say, the completion of the European Climate and Energy Modeling Platform event, all the presentations will be accessible. So the colleagues who are now present, or also other colleagues, will have this opportunity to go through your slides and raise additional questions. One question, if I may, is, are you using any other variables except for the weather conditions for the load forecast?
I'm using the load forecast posited by the system operator as an input. And what I find is that by including the forecasted meteorological conditions, I can improve upon that forecast. And then when I take into account the time series nature of the data, that there's pattern to the data that can be exploited to come up with more accurate predictions. So it's basically the two things. It's the forecast meteorological conditions. We all know that we're moving into a world where meteorology is more important. So what I'm trying to do here is take note of that. And then we also know that consumption is not purely random, that it has this systematic component. And so I'm exploiting that to come up with more accurate predictions. My apologies for not being able to show you the slide.
Okay, thank you, Kevin. And if there are no other questions, I don't see something in the chat. So thank you, Kevin. And now we will move forward to the last presentation of this session. When we share food, Sometimes the last one is unlucky. Maybe the piece remaining is smaller. But now Fabio is lucky because he will have more time than the others. So Fabio is a researcher at the IIASA, so the International Institute for Applied System Analysis, and Fabio Sfera will make a presentation about downscaling EAMS results to the country level, and he will present a new algorithm. So, Fabio, the floor is yours.
Yeah, thank you, Alexandros. Let me share my screen. Can you see my presentation?
Yes, yes, you can see your presentation. It's fine.
Perfect, thank you. Yeah, so basically today I would like to talk about downscaling internet assessment model results to the country level by using a new algorithm. So the main motivation for this is that internet assessment models are used in order to evaluate the feasibility of long-term Paris Agreement goal to keep global warming well below 2 degrees and to pursue effort to limit warming to 1.5. We have seen this morning the presentation from that left showing how internet assessment models are widely used in the IPCC. However, a limitation of internet assessment models is that they have a relatively limited regional resolution. So they usually focus on big regions like North America or Europe, but they do not provide country-level results in detail. So, for example, we don't have information of what Austria needs to do, or Spain, or Italy. Therefore, what we have tried to do here is to develop a new downscaling algorithm that allows to enhance the regional resolution of internet assessment model results. And the new downscaling algorithm focuses on energy variables, including final, secondary, and primary energy variables, and also on the energy-related carbon emissions. So here I would like to give you an overview of how the downscaling algorithm works. So on the one hand, we use data that are coming directly from the IAMs, internet assessment models, and then we combine this information also with the SSP data that we get with the GDP and population data that we get from the SSP database. If you're not familiar with this data set, I will encourage you to have a look at it because it provides a lot of information about GDP and population for all the countries in the world, and also according to different storylines. So basically, what we do here is to combine the storyline that we get from internet assessment model scenarios with the associated GDP and population projections that we get from the SSP. And then we also use additional data, in particular the historical data coming from the IEA energy balances. And we also use energy data from the Platts database regarding the currently installed power plants. And we use also additional data like governance indicators that are available at country level or supply cost curve. And the main idea behind the downscaling algorithm is that in the short term, countries will try to follow as much as possible the historical trends. But then in the longer term, they will gradually converge to the information that we get from internet assessment models. So we use what we call a sort of a conditional convergence approach. So we start with the real historical data, we try to follow the trend, and then we converge to the regional internet assessment model results. Also, when we downscale the regional IAM results to the country level, we take into account policies that are in place in each country. In particular, we consider the 2030 IDC targets and also the 2050 mid-century strategies. And then finally, we get the national pathways at the country level. So also to give you a little bit of a more detailed overview of what kind of variables we are downscaling, we start with the final energy variables, also with a breakdown by energy carrier, including electricity, solids, liquids, and so on and so forth. And then we also have the different sectors, including transportation, buildings, and industry. Then regarding the secondary energy variables, we essentially also split the data by fuel. In particular, for the electricity mix, we consider biomass, coal, gas, renewable energy, nuclear, in order to essentially see what is the electricity mix in each country. And then we also calculate the primary energy mix. And here we make a distinction also between CCS and non-CCS technologies. And this is particularly useful also when we calculate the total carbon emissions, because also we want to know, for example, what is the amount of carbon sequestration that is coming from biomass with CCS, because this leads to negative emissions. And also we want to know what is the amount of sequestration coming from CCS fossils. So those are the main variables that we are downscaling to the country level. To start with, I would like to give you a flavor of how we downscale total final energy, just to get an idea of how we do that. And to start with, I would like to start with this graph that shows the energy intensity in Europe. Each color here is a different country in Europe against GDP per capita. So essentially here you can see all the historical data from 1975 to 2015. And you can see that essentially, especially if we add additional countries outside Europe like China, India, and OECD, you can start notice that as GDP per capita increases, then the energy intensity declines. So basically we have this general tendency that higher GDP per capita also means a lower energy intensity. And this kind of trend is also confirmed by the internet assessment models. So for example, if we add here the baseline scenario from the message model, which is the red line, you can see that this will also continue from 2010 to 2100. So the main idea is that the higher is income per capita, the lower is the energy intensity. So as I mentioned before, what we are trying to do is to start with the real historical data. And starting from that, we try to get a sense of the relationship between energy intensity and GDP per capita. So we try to estimate some parameters. And basically, based on that, we create what we call the short-term projections that are based on the real historical data at the country level. And then we try to do the same thing, try to get the relationship between energy intensity and GDP per capita by using the data that are coming directly from internet assessment model, in this case, message. And this is what we call the long-term projections. And then we essentially make some convergence assumption, and we assume that we start from the short-term projections, and then we gradually converge to the long-term projections that are coming from IEMs. And of course, the speed of convergence here is a key parameter, because depending on the choice of the convergence, we can get a different result. We can get a different path. And essentially here you can see all the multiple lines that you see in the graph is a result with a different speed of convergence. And usually we determine the speed of convergence by looking at the robustness of the historical trend. So if we have a very clear, a very robust historical trend, then we assume a slow convergence. On the other hand, if the historical trend is not so clear, so we don't have very good data, then we assume a faster convergence to the regional IEM results. But this is, of course, a parameter that we can play around in order to get a range of projections at the country level. Then I also would like to give you an overview of how we downscale the secondary energy variables. In particular, I would like to focus on the electricity sector. And in order to downscale electricity, we use different criteria. One criteria is the historical data. So depending on what we observed in the past, we can allocate the results to the country level. Or we can use governance indicators. And this governance indicator is particularly useful for downscaling critical technologies like nuclear power plants, for example. Because here the assumption is that only countries that have a relatively high level of governance can actually, will be actually able to install those kind of critical power plants. Then we have the supply cost curve criteria that we use in particular for renewable energy, solar, wind, hydro, so on and so forth. And then the last criteria that we use is the plant capacity. So we look into what are the currently installed power plant. We calculate the remaining technical lifetime, and then also we look into what are power plants that are planned or under construction. And we use this as a criteria mainly for downscaling fossil fuel technologies. Now, to just give you a flavor of the results. Well, first of all, we can play around with the weights that we discussed before. So usually we use these criteria metrics that you can see here in this table. For example, for solar, we use 35% of the cost curve criteria, we use 50% of historical data criteria, and 15% of governance criteria. And if we apply those standard criteria weights, we get the results that you can see in the graph above. And here you can see the downscale results for all the different fuel under the current policy scenario from message, and also comparison with the real historical data from 1990 to 2010. If we play a little bit with the criteria weights and try to change them a little bit in a random way, then we get a range of results. And on the right-hand side here, you can see the distribution of the results in 2050 if we apply a range of criteria. And here you can see that the larger uncertainty in this particular scenario is for gas, because gas is increasing a lot in the region. And therefore, depending on how you want to allocate gas, depending on which criteria you use, you get a different amount in 2050. Then we move into downscaling primary energy and emissions. So here what we do is to simply apply some conversion factor to calculate, starting from secondary energy, we calculate primary energy by using those conversion factors. And here you have, for example, the downscale results for the UK and Germany under a current policy scenario with a breakdown by fuel, and also a comparison with the real historical data from 1990 to 2010. Then based on the primary energy mix, as I mentioned before, we calculate the energy-related carbon emissions, which is the graph at the bottom. And again, here you can see the comparison with the real historical data. So this is the current policy scenario, but what we can do is to apply the same downscaling method to downscale a 1.5 pathway. And if we do that, you can see that fossil fuels will be gradually replaced by renewables, and also energy-related carbon emissions will decline and reach net zero by 2050. So far we have looked into two main countries in Europe, the UK and Germany, but of course we can apply the downscaling algorithm to any region, and therefore we can downscale all the countries in the world. And just to give you an example of a region outside Europe, here you can see the emissions from CO2 energy-related CO2 emissions in the sub-Saharan Africa region. And this is a quite interesting region because at the moment this country is dominated by South Africa. In South Africa, we have the majority of emissions today coming from, in this region. But then in the future, Nigeria is projected to become more and more important, and by 2050 will become the major emitter. Then on the right-hand side here, I would like to show you another interesting region, which is China. This is very different from sub-Saharan Africa, because here we have a very dominant country, which is China, the blue area, and this country will remain dominant in the region. But then, of course, we also have additional countries like Vietnam, Hong Kong, Mongolia, and so on and so forth. Another interesting case, coming back to the Western European region, here you can see the breakdown of all the emissions at the country level. Today, Germany is the bigger emitter, but then in the future, Turkey, which is part of the Western European region of message, is projected to become the largest emitter in this region by 2050. And then finally, also, the last example that I want to give is the one of the Pacific OECD region. This region includes Australia, Japan, and New Zealand. Here, emissions in Japan are projected to decline over time, and this is mainly due to the socioeconomic projections, because population is projected to decline in the future, and therefore also GDP growth will remain relatively low, and therefore also the emissions will slowly go down even under a current policy scenario. On the other hand, in Australia and New Zealand, emissions will remain rather constant or even increase over time. Then jumping to the conclusions, so basically we are presenting a new downscaling algorithm that focuses on energy variables, in particular final, secondary, and primary energy consumption, and also the energy-related carbon emissions. The goal of this tool is to assess the feasibility space of the Paris Agreement by providing a range of pathways at the country level. A nice feature of the downscaling algorithm is that we also take into account country-level policies in 2030, basically the NDCs, and also the 2050 mid-century targets. And basically with this tool, we would like to provide a little bit of guidance to policymakers on how to enhance the current ambition of the NDCs and the long-term targets, because as we have seen in the presentation this morning, there's a really big gap between what countries have promised and what needs to happen in order to achieve the Paris Agreement. And with this tool, we can translate the results, the insights that we get from integrated assessment models to the country level, where essentially decisions need to be made. So yeah, with that, I finish. Thank you. Thank you very much.
Thank you very much, Fabio. Very nice presentation, and it's very important to to downscale to the national level. Now, okay, the floor again is open to the audience for questions. One question that I have is regarding the methodologies that you use for the convergence. What methodologies did you use, and how did you achieve the convergence between the short and the long-term projections?
Yeah, thanks. Maybe let me share again my screen so that we go back to the slide. Can you see my screen?
Yes, yes.
Perfect, thanks. Let me go to the convergence slide. Yeah, so oops, no, that was too. Sorry, I went to the presentation mode. Okay, so basically here, yeah, basically what we do here is to develop essentially two kind of downscale results. One is based on the historical trends, which is what we call the short term, and the other one is more based on the regional integrated assessment model results. And essentially here, the convergence, it is essentially based on the quality of the historical data. So essentially, if we find that there is a very good relationship in one particular country, for example, Greece or Italy, if we find that there is a very good relationship between energy intensity and GDP per capita, then we assume a slower convergence to the regional IM results. On the other hand, if we see that essentially the relationship is not so clear, in particular if the R square of the regression is not so high, then in that case we assume a faster convergence to the regional data. What do we mean by fast and slow? So basically, a fast convergence, it is essentially if we reach a convergence to the regional results by 2050. A slow convergence, it is something around 2200. So basically, really, far away future. But as I said, this is a parameter that we can play around with, and if we essentially we can get a range of projected results at the country level based on the same scenario for a given region. So it just changes how the results are distributed across all the different countries. Then you and another question about the methodology, right? Or was it related to the methodology of this convergence, or did you refer?
Yes, yes, this was about the convergence. I have one question regarding the. I have seen in a slide the cost curves, and you have assigned weights to the criteria. So, for assigning these weights, did you consulted the experts, or how you have used another methodology?
Well, yeah, that was actually a little bit of a discussion that we had internally with other colleagues, try to find out what would be, let's say, the best criteria. So essentially, it is also a little bit, so just to give you an example, for solar power plants, we are not looking into the plant capacity, because essentially, well, yeah, this is not really an information, because solar, it is essentially a new technologies. So if you look into the existing capacity and the remaining technical lifetime, such a criteria doesn't make so much sense, because essentially in all the countries it is a relatively new technology. On the other hand, this criteria is particularly useful for fossil fuel because, for example, China have very new power plants that have been installed around 20 years ago or even less. So they have an average technical lifetime which is much smaller compared, for example, to the US. US have the power plant lifetime of coal, it is around 40 or 50 years already. So basically most of them are almost ready to be retired, but they are not because they are still making money in a sense. On the other hand, in China or a country like China, which has those very new power plants, then it becomes more difficult to phase them out because they are still relatively new. So basically, the company need to get need to cover the investment. So this is the kind of a criteria that we use for downscale fossil fuels because there's more variety across the countries. Yeah, for the fossil fuel power plants. Also for the cost curve, for example, it doesn't make a lot of sense to do it for fossil fuels. We think this is something that makes more sense about wind, solar, and biomass because that is really dependent on the country. There are countries like Australia or Spain or Italy that have a lot of solar, and others like Finland, Norway that really don't have a lot of solar, especially in winter time, and therefore it doesn't make yeah, and therefore the cost curve criteria it is very useful for downscaling technologies like renewables, which are pretty much dependent on the country that you're looking at. For fossil fuel, you can install fossil fuel in any country without any particular problems in terms of the location itself. But we haven't done a broader consultation. We just discussed about it internally. I have to say, yeah, this is something that we could do definitely to have a better, yeah, to define better our standard criteria ways.
Thank you. Thank you very much, Fabio. So we have reached the end of this session. Many thanks to all attendees, speakers for the great presentation and fruitful discussions, and the organizing committee. And I suggest to all of you to okay, following a 15 minutes coffee break to join the closing session of European Climate and Energy Modeling platform. We are exactly on time. Thank you very much also for, let's say, for, for, for all the presenters for being on time. Uh, Thank you. Goodbye.
Thank you.
Thank
Bye
you.
bye.
Thanks.
Bye
Bye
bye.
bye.
Thank you.
Bye bye.
Bye.
Ciao.